right, live streaming is on. Hi, everybody. Thanks for joining us at the Atlantic time band of the ACM Student Research Competition Technical Presentation Round. We'll be getting started in about 5 minutes. So just sit tight, talk amongst yourselves. Well, really talk to yourself, since I don't think you can easily talk amongst yourselves for now. And then we'll have 2 presentations for you. So just hang tight. Hi, Yi.
Hi.
It's good to have you here. Just to let you know, you're being currently live streamed and broadcast. So we're going to get started in about 5 minutes.
Okay, thank you so much.
Would you like to practice putting your slides up on the screen?
Okay, I can try that.
Yeah.
Okay. Can you see the slide?
Yep, we can.
Present. Begin.
Yeah, go into presentation mode. Yep, works perfectly.
Okay.
Awesome. So just to let you know, for you, the instructions are going to be that when you are presenting, you'll share your screen and your camera and your microphone. When you're done and the questions are over, I'd like you to mute your mic and camera and stop sharing your screen.
Okay, no problem.
Great. So please stop sharing for now, and I'm going to put up a slide for the audience.
Okay.
That's going to introduce the session. Share. All right, so everybody, we're going to get started in 3 minutes. Hopefully my microphone is still working.
Yeah, it's working.
Good. Hang on a sec. Let's try this one more time. Let's see if this works. Perfect. Okay. Again, for those of you just joining us, welcome to the ACM Student Research Competition Technical Presentation. This is the Atlantic time band, which will begin in about 3 minutes. And my subtitles keep turning themselves off, so I'm going to disable that for now, if I can. Sorry, I just wanted to start, on time. 1 more minute, and then we'll get going.
Okay.
To introduce the competition to everybody, we've been having several rounds of competition. The first round was a several-page abstract that we had 30 submissions from our contestants that were evaluated by a program committee. Those that qualified were admitted into the competition that happened during the conference. Yesterday, we had a poster presentation competition round in which each contestant in all of the different 3 bands went and presented their posters to a variety of judges who entered their Zoom rooms. And the top 5 contestants in the graduate competition and top 4 contestants in the undergraduate competition were qualified for today's final round of presentations. In this round, each contestant will have 10 minutes to give a talk about their research work, and that will be followed by 5 minutes of Q&A. Each judge can type in questions into the text chat window for Zoom, and I will read them out loud to the contestant at the end of their presentation and ask the contestant to respond verbally so that you can hear their answers. You should, as judges, you should already have a score sheet available for yourself to record your responses. Immediately after the session is over, please fill out your scores and send them back to the co-chairs. In today's Atlantic time band session, we have our final 2 presenters. The first one is going to be Yi Li, who is a graduate student from the New Jersey Institute of Technology, who's going to be talking about improving bug detection and fixing via code representation learning. So let's have Yi take over and start his presentation.
Thank you. Thank you for your introduction. Let me sharing screen. Can you see my screen well?
Yes, we can.
Okay, thank you. Hi, everyone. My name is Yi, and I'm from the Space Lab in the New Jersey Institute of Technology. So today my topic is improving bug detection and fixing via the code representation learning. In our life, the software quality and reliability become more and more important. The bugs in the software often can cause a lot of serious problems. For example, they can cause the Uber self-driving car crash and lead to death, and they can cause a serious problem on the Houston rocket, or they can cause the Facebook and Google lost their user information and cause economic problems and security problems. So in order to deal with these problems, many developers developed several existing approaches to deal with the bugs in the softwares. And in this process, we call it the bug detect and fix process. So in this whole process, the input should be a project with some bugs, and with many steps after that, then we expect to get an absolute clean project without any bugs. And these several steps inside can be many sub-steps. These sub-steps including the bug detection, fault localization, automated program repair, concurrent testing, and so on. So among all these steps, deep learning approaches performs a very important role here because the rule-based or some simple learning-based approaches, they can not always generate enough rules or enough patterns or something to cover all the situations, but deep learning-based approaches can learn from the data and they can catch more information than traditional ones. So the deep learning approach, in some way, they can contribute in each step of this a lot. And as for the deep learning approaches in these whole areas, they often have the similar process, like they often analyze the code, then they do the code representation learning, and then they do it for different tasks, they use different models. Even the tasks are different, but they always have a same step, which is called the code representation learning. The code representation learning can be divided into 2 parts. One is called code representation, and the other is learning. So this whole process is used to transfer the information in the code to some way of representation and let a deep learning model can catch. The code representation can be the natural order of the tokens in the code, or they use the abstract syntax tree, or use some other code representation ways. And the learning is based on what kind of representation you choose. You need to choose a specific learning approach and a suitable learning approach to learn the code representation to make it suitable for the task. And among all the existing deep learning-based approaches, they all not really perform perfect on the code representation part. They always can have some use some simple code representation ways, which cause a lot of limitations. For example, as in the bug detection areas, they often only consider the existing, the current methods which we are checking, but they don't care about the code relationship. For example, if the method A called method B and method B is buggy, then method A should be buggy in some way, maybe. But because they don't analyze the relationship between this, so they have a hard time to detecting cross-method bugs. And as for automated program repair areas, the existing deep learning approach do is that they often feed the whole method as a big box into the model. Or they feed only the buggy code. Both of them, then they will lose the surrounding code context information. So based on this one, we found that the existing automated program repair approach often cannot work well on the modeling the buggy code and the surrounding context at the same time. So in order to overcome these kind of limitations, we come up with our own approaches. First one, on the bug detection areas, we have the following ideas. We firstly analyze the code structure and the code context in the method that we want to analyze, then to learn the local context representation. So this is just similar as the other existing work do, but we use a new way of learning the code representation. And also at the same time, we analyzing the code relationship to learn the global context representation. This can help catch the code relationship between different methods, a method call, data dependence, or something. Then combining these two learned representations, we can do the bug detection, which can overcome the limitation we mentioned. To be more specifically, when there comes a new project with two buggy methods, if we want to analyze method one, we firstly generate a long pass in the abstract syntax tree for this method. The long pass is the data structure we predefine, which is starting from a leaf node of the abstract syntax tree and then going up to the root node, then going down to the other leaf node. And then the next step is that we analyze the code relationship. Because we know that the first method get results, they call method calculate. So we can, when we generate we can use this kind of relationship to generate some analysis graphs, like the program dependency graph and data flow graphs. Then we put them together to generate this graphs. And then we use the long pass and the graphs we generated to get the local context and the global context. We have this kind of two representation, then we put them together to do the bug detection. In this way, we can overcome some limitation in the deep learning based bug detection approach. And as for the automated program repair approaches, our key ideas is mainly that we want to identify the code transformation in the surrounding context as the new code representation learning way. And at the same time, we use the code representation learning results to enhance the code transformation learning results. Here, the code transformation means that the learning the code fix, and the code context learning means that we want to learn the surrounding code context. And to be more specifically, when there comes a new buggy method, we know which line is buggy and other parts are not buggy. Then we firstly have one layer called context learning layer. Then we put the surrounding code context into that context learning layer. Then let it learn a weight, which can help the transformation learning layer. Then the next step, we put the weight and the buggy line together into the transformation learning layer. And then the transformation learning layer can learn the results combining both the surrounding context and the buggy line fixing. Then in the end, they generate a candidate patch list in order to do the auto fix. In order to evaluate if our new kind of code representation learning can really help on this two area. So firstly, we evaluate on the bug detection problem. We compare with all the state-of-the-art bug detection approaches, and we evaluate on a big data set, which contains 8 well-known open source Java project 92 versions, use F-score to do the evaluation. And the results can be shown here. From the figure, we can see that our approach is in the red box, and which is top one. And comparing with others, we can improve about over 160%. So as a summary, our approach can detect 70 to 160 bugs more than other existing approaches, which prove that the new kind of code representation learning in bug detection is really helpful. And then we evaluate our approach on the automated program repair substep. Also, we compare with the baselines, but we not only comparing with the deep learning based, but also comparing with some other pattern based, which is the traditional way of doing this. We evaluate on a famous data set defects4j, and we use the actual number of auto-fixed bugs to evaluate our final performance. As for the results, you can see in this figure, our results is here in the red box. Even our is not the best one, but we already can overcome most of the existing approaches. Only just a few less than the top one, which is T-bar. But as a summary, we want to point out that we are the first deep learning-based approach have the comparable results with the top perform the pattern-based approach. The top three, SimFix, Hercules, T-bar, all of the three are pattern-based, and the other deep learning-based are Ratchet, Cody, and Tufnell, which is on the very left part. So we improved the existing deep learning-based approach a lot. So for the future work, because we already proved that the code representation learning is really helpful, so we want to create more novel code representation, creating more novel deep learning model based on this representation, and apply this kind of representation learning on other subdomain, like the for localization concurrent testing we already mentioned. And as a summary, in this paper, we already introduced what is the code representation learning and what is the existing limitation for the code representation learning on the deep learning-based approaches in the bug detection and APR approach area, and how we build our own model to overcome this kind of limitation. And the experiment also shows that our new code representation is really helpful. And then we introduced a little bit about our future plan, future work. So this is all about my presentation today. Thank you very much for your listening and questions.
Great, thank you, Yi.
Thank you.
So we have a first question is, what types of bugs does this approach detect? Are they simpler syntax level issues, or are they more complex, like concurrency bugs or security bugs?
Because when we learn the model, we don't split the bugs into different types. We directly learn from all different types of bugs. So based on our experimental results, we can detect some syntax bugs, also can detect some more complex bugs like the logistic bugs and the security bugs. Yeah, but it depends on how we use, what kind of data we use. But at least in our data set, we can detect part of the all kinds of data, all kinds of bugs.
Okay, and are those bugs different or orthogonal to those found by pattern-based approaches?
Yes, exactly. The existing approaches, we especially can detect many the cross-method bugs, as we mentioned. This is the key limitation we want to overcome. I think among all the bugs we detected is about 10 to 20% bugs are the cross-method bugs, and other existing approaches cannot do that. So we detect new bugs than other approaches.
Great. Are the code structure and context representations learned together under the same loss function? Or how does your loss function capture the goals of the two different approaches?
You mean in the bug detection problem?
Yes.
Yeah. Yes. So in fact, we use the long pass to represent the local context, which is the code structure and code context. And this kind of the long pass is as we predefined, it starts from a root node, from a leaf node going up to the root node and going down to the other leaf node. This long pass can represent how the structure of the current method and what the actual context in the code. This is for the local context, and for the global context, we directly use the graphs and use the node to vect, which really don't care about what information contains in the node. They're only capturing the relationship. By combining these two things, we use the multi-head attention tool to also called transformer tool to combining these two things. This attention layer can help us pick out the useful information. And in this way, we use one loss function to capture both the global context and the local context.
Great, thank you. And one last question. Do you have any thoughts or insights, either from what you've done or previous work, on whether the challenges here are a product of the representation or are caused by the learning method that you've chosen?
Or you mean the challenges? Yeah. Yes. The challenges in the bug detection part, then the most serious challenge is that because some kind of bugs is uncommon and the model learning cannot really catch it, and sometimes the bugs have even we try to build a big graph, but the relationship between different methods can be a very complex thing to analysis. Simply using a graph maybe we have proved that it's useful, but maybe we can do more future work on it to split it down, maybe become a smaller subgraph, then may have a clear analysis on that. This is one challenge, how to analyze the relationship clearly. And as for the APR approaches, the most challenging thing is that for now, our approach can only fixing one statement bugs, which other baselines almost can do the similar thing. It is really hard for the existing approaches to fix the multi-line bugs because the situation has become more complex. We are trying to generating more novel code representation learning ways to get a representation for the multi-line bugs in order to fix it. So this is the most challenging thing.
Great, thank you so much.
Thank you.
And I'd like to thank Yi for his presentation today.
Thank you.
So please stop sharing your screen and
Yes.
mute your mic and camera. And we're gonna switch over to Zhenhao Li, who is a graduate student from Concordia University, who's gonna be talking today about studying and suggesting logging locations in code blocks.
Hi, so I'm gonna share my screen.
Yep, we can see it.
Okay, so I'll start. So hi everyone, my name is Zhenhao, and currently I'm a first-year PhD student at Concordia University, supervised by Dr. Peter Chen and Dr. Wei Shang. And today the title of my study is Studying and Suggesting Logging Locations in Code Blocks. So when a system is running, it may generate blocks, which show the execution behaviors of the system. And as you may know that logs are pretty important for developments and also operations. They're usually used by developers to do debugging and also by operators to do the system monitoring. So logs are often treated as the most important or even the only source of information for debugging and maintenance. And not only limited to system debugging, logs can also be used in a variety of tasks by applying some specific analysis, such as performance analysis, user requirement tracking, understanding the program, and verifying the system. And logs, the general logs are generated by logging statement, which is a snippet of code that generates logs. It may contain a verbosity level, which is a warning level here, and some static messages, which is cannot parse job ID from here in the example, and maybe also some dynamic variables, which are path and a stack trace E here. So if we have many logging segments, then we may have plenty of system execution information to report. But the problem is inserting too many logging segments may also increase system performance overhead and produce many trivial logs that may mask the real problem. And in contrast, if we insert too little logging segments, then we may not have enough execution information to analyze and further do error diagnosis. Some prior studies try to provide suggestions on deciding logging locations, but they're either very coarse-grained, like suggesting you in which method to insert the logging segment, or even in file level. Or some other studies provide suggestions only for some specific situations, such as catch blocks and return value checks. So the decisions on logging locations are still a very challenging task, and a finer grained general support for where to log is needed. So in our study, we first extract the logging segments with their surrounding code from 7 open source systems. And we randomly sampled some logging segments with a 95% confidence level and 5% confidence interval to manually study the characteristics of their locations. And from our manual study, we find that developers often log information in code blocks, such as an if statement or a for loop or catch clauses, something like that. And they may leverage the syntactic information, semantic information in the source code, or both to make logging location, or to make the decision of logging locations. And we will explain what is syntactic and what is semantic later. So driven by our manual study, we propose a deep learning-based approach to suggest logging locations at block level. We first extract 3 types of code block features from the source code. They are, just as I mentioned just now, syntactic, semantic, and the fusion nifty above 2 features. Then we give a very simple example of how do our code block features look like. So here is an if block with a method invocation as its condition. And the block contains a logging statement, a log.arrow, a method invocation handle arrow, and also a return statement. So first, when we are extracting the features, we have to remove the logging statements first to avoid a bias. And then we illustrate how do we get the features for each line of code. For the first line, the if statement and its condition, we will get its syntactic tokens like this. So basically if statement and a method invocation. And its semantic tokens like this. So note that we do stemming first for the tokens in order to reduce the size of vocabulary. And we also filter the structural tokens like such as if to avoid any overlap with the syntactic feature. And for fusion tokens, basically it's a combination of the above 2. Then for the second line, it's similar. And for the last line, we got a return statement for syntactic and the fusion feature. Then we feed our extracted block features to the framework, which is an LSTM-based framework. So given the block feature, our approach will suggest whether this block should be logged or not. It's actually a binary classification problem. And we propose 2 research questions to evaluate our approach. For RQ1, it's how effective are different block features when suggesting logging locations. Basically, we evaluate the performance of each block feature on different categories of code blocks, like try-catch blocks, branching blocks, such as if and switch, and looping blocks, such as for and while. And as shown in the bar chart, the syntactic feature, which is the blue bar here, achieves the best balanced accuracy for all the categories of blocks. So probably we can say that models trained using the syntactic block features achieve the best results. And syntactic information might be leveraged to suggest logging locations. Then for RQ2, are the trained models transferable to other systems? In this RQ, we actually do cross-project predictions to see whether the models can also work well on other systems. We compare the balanced accuracy of cross-project prediction, which is the green bar here, with the performance in RQ1, which is the blue bar here. And we then compute the ratio of the cross results against the within project prediction results, which is the red number above. So we can see that the ratios are above 90% in all the study systems. So probably we can say that cross-project suggestions also have a good performance, similar to the performance in RQ1. And it's also possible that developers in different systems may follow some certain implicit guidelines on deciding logging locations. And maybe future studies can try to go further on this direction. Then to sum up, in this presentation, we talked about the wide usage of logs and what is the logging statement and the trade-off of logging. And prior studies provide limited support on deciding logging locations, which makes it still a very challenging task. And we then propose our deep learning-based approach to provide a finer-grained, more general support on deciding logging locations. So that's the presentation. Thank you. Any questions and suggestions?
Great, thank you, Zenhali. I have a question here. If I'm understanding correctly, you were using the current log locations as the ground truth. What evidence do we have that developers are currently using logging effectively? In other words, is it possible we are training a system to log poorly, just like current developers?
Yeah, it's also possible that developers didn't really follow a good practice to make the logging locations. So in order to avoid or reduce the impact of this, we use the mature open source large-scale systems, which has many years of maintenance history. So we believe that they have very good logging. They have following very good logging practices to use it as our training data.
What is the scale of the number of logging statements that are in those sample code bases?
The scale of the sample?
Yeah, like how many logging statements are in each generally?
So in general, there are thousands of logging statements in each system. And overall, because we have 7 study systems, so overall there are probably around 10,000 logging statements in total. And we, as we mentioned just now, we use 95 confidence level and 5 confidence interval to make the simple sets. So after the sampling process, we have around 375 total in total logging statements as our sample set.
Great. What is the false positive and false negative rates in your work?
The false positive and false negative?
Mm-hmm.
Yeah, because we only showed a balanced accuracy in the presentation because the spaces are limited. But in the paper, we do mention our precision and recall rate. So I remember they are around 60% in average for precision and recall. And probably we can show the false positive rate and false negative rate for the results.
Okay. In the example code block, would it be biased if we just removed the logging statement? Is it possible that the whole block is created because the developer decided to add a logging statement to that block?
Yeah, there are some blocks that are only intended for add logging statements, such as, log guards. Like the condition is just if the bug is enabled or if the trace is enabled. So we do notice there are some blocks like this. So we filter the blocks like this in order to reduce the impact of the bias of blocks.
Great. Did you try any other types of machine learning techniques before going to deep learning? Would a simpler representation suffice for predicting these logging locations?
So far, we haven't tried some like traditional machine learning approaches, but I think it might be interesting to try them as well. But when we are starting the project, we just want to start from the state of the art, which is deep learning here. So we just use the LSTM framework, which is good at processing the sequential data, and the source code is also sequential data. So we choose to use LSTM as our start. But I agree that it might be also interesting to see how the traditional approach go on this task.
Yeah. How long did it take to train these models? I mean, deep learning can be kind of expensive performance-wise.
yeah, it depends on the size of the systems. So for some smaller sized systems like Zookeeper, it may take just a few hours to train the models. But for some large ones like HBase or Elasticsearch, it may take half of a day or even more than a day to train the models. So it depends on the size of the system.
All right. One final question. Have you considered how you might present these suggestions to developers in such a way that they would actually add locking statements where you suggest? There is probably a lot of evidence that developers tend to ignore recommendations from automated systems.
Yeah, actually, we were considering to conduct like a user study to practitioners, developers, or other researchers to see if our approach is really useful or not. But so far, we haven't really done it. But I think it might be useful and helpful to collect the feedback from the real users to see whether they will just ignore our suggestions or they think they are useful. So maybe we'll do a user in the future.
Great. So that's all the time we have today for questions, but thank you very much, Zhenhao. We appreciate your talk. That was very good. And that is it for our session today. We only have 2 presenters, and these were the final 2 for the round. So in just a few short hours, we'll be tabulating the results and announcing them at the award ceremony at the in the next Pacific time band on July 10th, which is going to be at midnight UTC. So everybody, please join us there to hear the results. And in addition, if you have free time, come join everybody at the coffee chats or in the video lobbies in clouder.org. They tend to be kind of fun. So thanks very much, everybody, and we are signing off for today. Judges, please do send your score sheets as soon as you can. Thank you. Bye.